us talk about another question. We shall talk about question number 5, which is saying the set of all real numbers are except 0 under the operations defined below form a vector space. We have addition for any xy picked from R minus 0 for any vectors picked from this. X plus y will be same as x dot y, that is x times y. A scalar multiplication for any k picked from F and x picked from R, then we shall have k times x equaling to x to power k. So this is the definition for addition and scalar multiplication, and we want to show that this one here forms a vector space, and we shall prove that by proving all the 10 axioms that we have clearly seen. So beginning with the first one, basically we shall use these elements, that is x, y, and z will be picked from our given set, that is R minus 0, and we shall have k1 and k2 picked from F, picked from the scalar field, that is the field F as clearly given. So we are picking x, y, and z from this, and we are picking k1 and k2 from the field F. So we need to show that this one here forms a vector space under this addition and scalar multiplication defined here. So let us see whether it satisfies this space here satisfies the 10 conditions for a vector space. So we shall begin with number 1. Our number 1 is about closure. So number 1 is about closure property, that is closure. So I will simply talk about the closure property. So closure property, that is, we need to show that it is closed under addition, and for that case we need to pick any two elements from this set, that is, for example, x plus y. So we need to show that x plus y is also in this vector space. So looking at this x plus y, by definition, let us look at by definition. Remember, you have to use this definition. They said that x plus y is same as x times y. So by definition, x plus y is same as x times y. This is same as x times y. Now, for that case, we have seen that x plus y is equal to x times y. But our interest is x times y also a real number in this given set? That is true, because when you get 2 times 3, this is a real number, this is a real number. It will also give you 6, which is a real number. So when you multiply real numbers, you will get a real number. So that's why we say that x plus y equaling to x times y, this x times y is automatically an element of R minus this 0. So if this is true, that x times y is an element here, then we can conclude that x plus y is an element of R minus 0. And the closure property will be satisfied. The next axiom is about commutativity under addition. So we need to prove this one here. So what do we need? We need to show that here we need to show that when you get x plus y, it gives you y plus x. So let us begin with x plus y. So if you begin with x plus y, what is x plus y? X plus y is same as, look at the definition. They are telling us that when you are adding x plus y, it is same as x times y. So by definition, this one here is same as x times y. So this is x times y. But if we have x times y, can we say that this is same as y times x? Because we know that if you are multiplying two real numbers, x and y, then it is same as y times x. If you are multiplying 2 times 3, it is same as 3 times 2. So if I have this, I can as well write that x plus y by definition is x times y, but x times y can be written as y times x. And if this is true, what is y times x? By definition, this is still same as y plus x. So if this is true, it implies that x plus y is same as y plus x. And this will be proved. So we are proving this using the definition for the scalar and scalar multiplication and addition. So you have to define or to be adding the same way you are given. So that's why that's what we were doing in our example number 1. So you use the addition that you are given. So use the operations given in the proof. So that is what we have for commutativity and addition, and that will be proved. So let us talk about the next one, which is associative and addition. So under this, we are interested in x plus y plus z, which is same as x plus y plus z. So we need to show this. If we need to show this, then we shall start with one side. So let us consider x plus y plus z. By definition, what is x plus y? By definition, this is same as x times y, but we are adding there z. This is what we have. X plus y, by definition of addition, by definition of addition here, x plus y is same as this. So if that is the case, so it means we shall have x times y plus z. But this is one value plus z. So by addition, we can also say this is same as, this one here is same as x times y again times z. We can write that. Now, if we have this, we can still write this is now multiplication. So we can still write this as x times y times z. We can still write this. And if this is true, still we can again write this as, this is times here. So I can again write this as x plus y times z. So this is by again definition of addition. If we are multiplying, then we add. So if I have this, I can still write this as x plus y times z is same as y plus z. So clearly, you have this, which is equal to this, and this axiom will be approved. That is associativity and addition. We have so far talked about 3 axioms, that is closure property, commutative property and addition, associative property and addition. So we want to look at the first axiom, which is identity for addition, or what we normally call the additive identity. So we need to show that there exists an additive identity within that given set. Now, we shall let x prime to be an element in R minus 0, be such that for every x we pick from the same set, it will hold that when you get x plus x prime, you get x which should be same as x prime plus x. We understand that for additive identity, this property must hold, that when you get x, an element in this given set, you add there the identity for addition, which we are calling x prime, you should be able to get x. That is by definition. But this should as well be same as having x prime plus x. So this must hold for x prime to qualify to be called an additive identity. So for that case, if we let x prime to be an element within R minus 0, such that this one is satisfied. So it means when we talk about x plus x prime, which is equal to x, so we know that by definition, what is x plus x prime? By definition, x plus x prime, when you look at this addition, when you are adding x plus another value y, which is picked from R minus 0, then you should be multiplying the two. So this is by definition that x, when you are adding, is same as multiplying. So for the same case, we shall also say by definition of addition property that is given, then this should be x times x prime. So in other words, if this is equal to x times x prime, then can we say that this x times x prime is also equal to this? Because we are having this and we are having this. So we can easily say that 1 is actually equal to 2, which means that since x plus x prime, for x prime to hold as an identity, must be equal to x, then it means that this x prime is also equal to x. And for that case, it means x prime is actually 1. So it means that our additive identity for this case is actually 1. And when we look at this one here, actually 1 is an element of R minus 0. So clearly, we can easily see that 1, which is an element of R minus this one here, we can easily say that the additive identity exists and it is 1. You can easily prove that by looking at this one here. When you get x plus 1, does it give you x? By definition, we know that x plus 1 is same as x times 1, and which is same as x. And the same is also, if you get 1 plus x, this is same as 1 times x by definition. So which means that 1 plus x is actually same as x. So clearly, we can say that the additive identity exists and it is a real number which lies within this given set. So if that is true, then we can say therefore the additive identity exists and it is 1. Which one is an element of this given set. So an additive identity exists within this set. So that property will be satisfied. So that is for additive identity. Then we can look at the next property as well. Number 6, we look at axiom number 6, which is about additive inverse. Additive inverse. So from the definition, we know that for the additive inverse, if, for example, we suppose that for every x picked from R minus 0, that is a set of real numbers excluding 0, there exists, suppose we say that for every x picked from this, there exists an element y from that same set, such that for additive identity, we looked at the case that it should be x plus x prime. That is, if x prime is our identity, then that when you pick any element from this given set, you add there that additive identity, it should give you the same element. However, when we talk about the additive inverse, it should hold that if this x is any element from this given set, then if we call this one here an additive inverse, then it should satisfy this given property. That when you get this x element from here, and this y is our inverse, if you get x plus the inverse, you should be able to get the identity. You should be able to get the additive identity. So in other words, when you get any element from this set, which is this one, then you add there the inverse, you should be able to get the identity. So this is what we are calling an inverse. So we are interested in knowing what is the inverse of each element within this given set. Then when we talk about the additive identity, we want to know what is the additive identity for each element in this given set. If it exists, what is it? So for this case, we have seen that 1 is our additive identity. So we want to look at the additive inverse. So we are asking, what is the additive inverse? And we are saying that for additive inverse, it should be able to satisfy the property that when you get any element from this given set, you add there the additive inverse, it should give you the identity. But we have seen that if we say x plus y is equal to, what is our identity? Our identity, we had let it to be x prime. And so we shall have this as x prime. But fortunately, we already know x prime. So we are saying that x plus y is equal to 1. Remember, our identity here, we got it as a 1. This is our identity. So if this is our identity, then clearly we can call this x prime, we can substitute it with 1. So let us look at this. We know by definition that x plus y is same as x times y. That is by definition of addition in this given set. That is what we were given. That whenever we are adding x plus any value, then it is same as x times y. This is by definition we are given. So here we shall say, but x plus y is same as this. So in other words, we can say from this and this that it will imply from 1 and 2. From 1 and 2, it implies that if x plus y is equal to 1 and x plus y is x times y, then it implies that xy is actually equal to 1. So it means that y is 1 upon x. So it means that our additive inverse exists and it is 1 upon x. So for any value that we pick in a set of real numbers other than 0, then it will have the inverse, and that inverse will be the reciprocal of that same element. So in other words, if you pick a 2 in a set of r minus 0, it means that in this set of real numbers, you are excluding 0. You are excluding 0 because if at all x becomes 0, it means this will be undefined, and for that case, it means there won't be an inverse, and we shall also not have this given space as a matrix space, as a vector space. So for that case, we are saying that for x is taking any value or any real number other than 0, the moment it becomes 0, then this one will be undefined and we shall not have an inverse. And if any of the axioms don't satisfy, then automatically it will not qualify to be a vector space. So we are saying y is equal to 1 upon x, that for every value you pick in r minus 0, for example, we pick a 2, then the inverse of this 2 will be a half. So that is 1 upon x, the reciprocal of that. In that, by definition, when you get 2 plus a half, by definition, it is 2 times a half. That is by definition of the addition in this given space. So which is same as what? Which is same as 1. So clearly you can see that for every element, when you add its inverse, you get an identity, which identity we have got as 1. So clearly this will be our inverse. So the inverse exists. The inverse, that is the additive inverse, exists because we know that this is an element of r minus 0. This one here, 1 upon x, is an element of r minus 0. So the additive inverse exists. So that is 1 upon x, which 1 upon x is an element of r minus 0. So this one here is the additive inverse for each element x picked from this given set. Now we are done with axioms related to addition. So we shall talk about axioms related to scalar multiplication. So number 6, we shall talk about scalar multiplication. Scalar multiplication. Number 6, we talk about scalar multiplication. So for this case, we are interested to show that for K1, which is an element of F, that is from the field, if we pick X from the set R minus 0, then we need to show that K1 of X is an element of R minus 0. That is what we want to show. That is when we multiply the scalar with this element from r minus 0, then we should be able to get this. So this is our point of interest. But let us look at the definition. According to the definition given, they are saying that the scalar multiplication, you should have k picked from f and x picked from r minus 0, such that k times x is actually same as x to power k. In other words, when you are multiplying a scalar with x, which is an element of r, you should have x to the power of k. So we shall be using this definition when we are dealing with a scalar and an element x or a vector x of r. So let us look at how to deal with the scalar multiplication. We need to show this. We need to show that. So we shall start with for k1 of x, for k1 of x, it will be same as, by definition, we have seen that by definition, if you have k which is in the field f, so it means when we look at this k in the field f, then k times x, it will give you x to the power of k. So we shall say here that k1 of x is same as x to the power of k1. That is by definition. But when you look at this, this is x. X is an element of R. K1 is an element of the field. The field, that is the set of real numbers. So if K1 is a real number, X is also a real number. So it means X to power K1 will also be a real number. And for that case, it will also lie in this given set. So that is for our case of K1 of X. So for any value of K that you will put here for X, x, which is an element of r minus z. So even if k is 0, it will be x to the power 0, which is already 1, and 1 will lie in this given set. So for any value of k1 that you substitute here, which is a real number, and x, which is also a real number in the set, this one here, then this one here will also become a real number, which real number is in this given set. So for that case, it means x to power k minus 1 is an element of this. If that is true, then it implies that k1 of x is an element of r minus z. And that will be proved. We look at number 7. Axiom 7, we shall be talking about a distribution So we shall talk about distribution of multiplication over addition. So here we are interested if we have a scalar, for scalar k1, which is picked from the field F. Then if x, y are picked from our set. So what are we interested in? We are interested in showing that k into x plus y is same as kx plus ky. We are interested in this. So let us look at that. Our k, for this case, we are using k1. So let us maintain k1. So we need to show that k1 into x plus y, same as k1 of x plus k1 of y. So let us look at k1 of x plus y. This one here, by definition, remember that by definition, if you have k times x is same as x to power k. That is by definition of scalar multiplication. That is what we are given. So if this is by definition, then we can say that k1 of x plus y is same as x plus y to the power of k1. So if this is the case, we can say that also when we are dealing with addition of two vectors from r minus 0, by definition of x plus y is same as x times y. We are getting all this from here. Definition of x, the vectors x plus y is here. You do multiply x times y. If you are having a scalar, you get x to the power of k. So that is what we are using. So by definition, this one alone, is same as x times y, but we are powering this by k1. So we are having that one. So we know that if we are dealing with, of course, multiplication here, this is same as x to the power of k1 times y to the power of k1 when we open that bracket. So from there, we can still say that this is also same as when you are multiplying. If you are multiplying, this is one vector, this is another one. We can still say this is x to power k1 plus y to power k1. This is by this definition again. If you have x times y, it is same as x plus y. So x times y is same as x to power k1 times y to power k1 is same as this by this definition here. So from here, we can still say that this is same as, what is this, x to power k1. If you say k times x is same as x to power k. So if I have this, I can still write this as k1 of x plus k1 of y. So clearly, you have shown that k1 into x plus y is same as k1 of x plus k1 of y. And this will be satisfied. Let us talk about axiom number 8, which is still about distributive property. But for this case, we are considering two scalars. So if we consider two scalars, k1 and k2, to be picked from the set F, then we also consider x to be picked from our non-empty set, which is the set of real numbers minus or except 0. So we need to show that when you get k1 plus k2 is 2x, you will get k1 of x plus k2 of x. This is what we need to show. Now we shall start with this side. Let us begin with k1 plus k2 of x. By definition, you know that by definition for scalar, if you have k times x, this is same as x to power k. If you have x plus y, this is same as x times y. That is by definition of the scalar multiplication and addition of the vectors within this given set. This is how it is defined. So for this case, this is same as x. By definition, these are scalars. This is a vector. So by definition, which is this, if you have scalars multiplied in a vector, then you get a vector to the power of k1 plus k2. This is what you get. So clearly, we have x to the power of that. But we know from the definition, if you are having powers, this is the base. So you are having powers, but in the powers you are adding, then this is same as having x to the power of k1 times x to the power of k2. So if you have this, still you will get this one here, because we know if we have the same bases, then we simply add the powers. So if in the powers we are adding, then we can multiply the bases. So this is true, and if this is true, we looked at the case that this one here, that x to the power of k is an element. This one here is an element of r minus 0. Still, this is also an element of r minus 0, meaning this is a vector, this is also a vector. So we have seen that if you are adding vectors, two vectors is same as multiplying. So if I'm multiplying, it is same as adding. So meaning that I can write this as x to power k1 plus x to power k2, because we have clearly looked at a scalar multiplication, and that property said that if you have x to the power of k is an element of r minus 0. So this one is also an element of r minus 0. So this is a scalar, this is a vector, this is also a vector, and the addition of two vectors is same as multiplying. So if I'm multiplying, I can add the two vectors. So that's why we are adding here. And this will be same as still. When I look at this, this is also x to the power a scalar. So it is x to the power k. So if I have x to the power k, I can still write this. This is an equivalent expression. So I can write this as k1 times x, plus I can write this as k2 times x. So clearly, we can say that x1 plus x2 of x is same as k1 of x plus k2 of x. And this property will also be satisfied. Let us talk about axiom number 9. You recall from our summary of axioms, axiom number 9 is if you are having a scalar, then a scalar times another scalar multiplied with a vector, you should be getting two scalars multiplied with this. So we are aiming at proving this, which is associative property of multiplication. So to look at associative property of multiplication, we are interested if we have k1, k2 picked from the set which is F, a set of scalars, and X is an element or a vector in R minus 0, then we need to show that this one holds. We need to show that this one holds. So to show that this one holds, we shall write K1, K2 of X. We shall consider this to give us this. So when we consider this, when we look at this, our definition, they say that if we have k times x, it is same as x to power k. If you have x plus y, it is same as x times y. That is by definition. So if this is by definition, let me first show you how this one is coming about. So by our definition, we are talking about the definition for addition and the definition for scalar multiplication. So by this definition, we can surely write this. But if we also try to relate what we are given with what we have, we can easily say that this one here is a scalar multiplied with a vector. So, and we are saying a scalar multiplied with a vector gives you this. So we shall say this is k1 times x to the power of k2. This is by definition now. Also, you recall very well, we said x to power k is an element in R minus 0. That is axiom number 6 for scalar multiplication. We said that this one here is an element of this. If that is true, then this is a vector from this given set. Now, if that one holds, then it means that this one here is a vector. And if this is a vector, then we can as well write. So we are having k1 times a vector. This is a vector, so we shall consider it in this form, k times x. So we shall have this as x to power k2, but the whole of this to the power of k1. This is one single vector multiplied with this. This is by this definition. So if that one is true, we can now write this as x. When I open this bracket, this will be same as k2 times k1. And this is actually same as writing k1 times k2. Since k1 and k2 are n real numbers, so you can easily do this. So if that is the case, also by definition, remember this is k1 times k2. So if you get a number like 2 times 3, you will get a what? You will get like 6. So this is like a single number, which is a scalar now. So a scalar times x, x to the power of a scalar can be related with this. So if you relate it with this one here now, when you have x to power k is same as k times x. So I can as well say this is k1, k2 times x by definition of the scalar multiplication. So clearly, we can conclude that k1 into k2 of x is actually same as k1, k2 of x, which is proved. So lastly, let us look at the last axiom, axiom number 10. So for axiom number 10, it says for one picked from a set of scalars, f, and x picked from the given set, then we shall need to prove, we need to show that when you get 1 times x, it will be same as x, which is actually same as x times 1. So you need to prove that 1 times x will give you x. So let us look at for 1 times x. By definition, remember that if you have k times x, it will be same as x to power k. If you have x plus y, it will be same as x times y. So if I have 1 times x, I can write this as x to power 1. But if I write it as x to power 1, what is x to power 1? X to power 1 is same as x. So clearly, we can see that this one holds. This one holds for every x picked from this given set. So for that case, if this one holds for all the values of x, then this one will be true. And if that is true, we can clearly see that all the 10 axioms have been satisfied. Thus, the set of real numbers, r minus 0 under the defined operations, of addition, under the defined operations of addition and scalar multiplication, and scalar multiplication, and scalar multiplication forms a vector space. So that will be the proof for all the axioms to show that this R minus, that is a set of real numbers excluding 0 under these defined operations, forms a vector space. So to summarize up, we have so far looked at given spaces and how they can form vector spaces under some given operations of addition and scalar multiplication. But let us look at some of examples where we might not form a vector space and why. For example, let us talk about the set of all integers. If we want to show that this set of all integers here, with the standard operations of addition, we know how to add integers, and scalar multiplication, we want to see that does this set form a vector space? Does it form a vector space? And which axioms will not hold? So as we are concluding, for you to show that a given set forms a vector space, it must satisfy all the 10 axioms. It must satisfy all the 10 axioms. If one fails, or more than one fails, that is some axiom which fails, then that one does not qualify to be a vector space. But let us talk about this set here. A set of integers, you know, integers can have -3, -4, negative, and so on. -2, -1, 0, 1, 2, and so on. These are integers. Now, if we look at standard operations of addition, it is very true that when you get an integer, that is, if A and B are picked from a set of integers, then it is true that when I get A plus B, I will also get an integer. In other words, when you get 2 plus 1, you'll get 3, which 3 is an integer. That is true. When you get 2 plus 5, it will be 7, which 7 is an integer. So that is also true. So clearly, when you add integers, when you add an integer with an integer, you will get an integer. So that one holds, which means the properties of addition will hold. The properties of addition will hold. So if the properties of addition holds, let us look at the properties that correspond to the scalar multiplication. Remember, we have axioms which are in two categories. We have axioms in two categories. We have axioms under addition. We can say that for a set, when we talk about a set of integers, clearly when you add an integer, if u and v are integers, if you add u plus v, clearly it will also be an integer, because an integer plus an integer, it will give you an integer surely. Then it means this will hold, this one can hold, so you will also be able to get a 0 vector, and this one additive inverse will hold. But when we talk about axioms of scalar multiplication, when you get A from any given field, F, then you multiply it with a number, for example u, which is picked from a set of integers. can it really give you an integer? We shall look at an example. A can be any real number. If, for example, I get a half picked from a set of real numbers, then if I use an integer, for example, a number like 3, 3 is an element in a set of integer. So when I use like a 3, then it means I want a times u. A times u is same as a half times 3, which will give me a 1.5. And 1.5 is not an integer. 1.5 is not an integer. So clearly, a closure under scalar multiplication, this axiom here will not be satisfied. So if this is not satisfied, so there is a high possibility that also some other properties that correspond to closure under scalar multiplication might not be satisfied. But this one will be enough to tell that our given set is not what? Is not a vector space. Because we can easily say that not all the values, not all the scalars that we multiply in an integer, we shall automatically get an integer. So that is not true. So the closure under scalar multiplication will not satisfy. And if it is not satisfying, then it is enough for you to conclude that the set of integers under the standard operations of addition and scalar multiplication is not a vector space. So this one here is not a vector space. Is not a vector space. So for you to confirm that it's not a vector space, one of the axioms should be able to fail. So if it fails, then it will be enough for you to conclude that it is not a vector space. So using these given hints on how to form a vector space, you should be able to try some of the few numbers here. You should be able to show that some spaces here should be able to show that this R2 with the defined operations of addition. For example, for this, it is defined in this form. You should be able to show that it forms a vector space. This one, we have looked at it, should be able to form also the set of polynomials in x over f over a finite degree of finite degree. We need to show that they form also this given set here also forms a vector space under operations of addition and scalar multiplication. We talked about this space here. We talked about this space, so you should be able to know how to define the operations of addition and scalar multiplication. Then next, you should be able to also deal with this given space, that is the matrix space. So you should be able to show that the matrix space of the set of all m by n matrices under addition and scalar multiplication defined as this should be able to form a vector space. Then also you should be able to try number 6. So you try this and come up with some good proofs of all the axioms. Let us now talk about the linear combination, and we shall say that if V is our vector space over the field F, and you pick a vector V from this vector space, then this V will be a linear combination of the vectors u1, u2 up to um. If we have scalars a1, a2 up to am in the field F, such that this V can be written as a1 u1 plus a2 u2 plus up to am um. So if you are able to write V as a combination of the scalars with these vectors here, then we shall be able to say that V is a linear combination of vectors u1, u2 up to um. So what you are interested in is to express a vector v which is from this vector space, so as a combination of the scalars and the vectors. So if this one is able to happen, if you are able to write v as a combination of scalars and vectors, then you will be able to say that v is a linear combination of such vectors u1, u2 up to um. So in other words, v will be a linear combination of these vectors u1, u2 up to um only when we have scalars, defined scalars, that is a1, a2 up to am, such that you are able to write this one here. So if you are able to write v as a combination of scalars and vectors, then v will be a linear combination of such vectors. Alternatively, you can say v is a linear combination of these vectors u1, u2 up to um if there is a solution to the vector equation. In other words, when you are able to solve this vector equation, that is v equaling to x1 u1 plus x2 u2, where x1, x2 up to xm are the scalars. So if you are able to solve this, or if this vector equation has got a solution, then you will be able to say v can be expressed in terms of a combination of these vectors u1, u2 up to um. We shall look at examples to understand better what is a linear combination. So let us look at this example number 1. Show that this v here, which is picked from R3, is a linear combination of these vectors u1, u2, and u3. So to show that, what are we interested in? By definition, we must show that this v can be written as a combination of u1, u2, and u3. So if that is the case, let us look at the solution. We shall say we seek for the scalars. We seek for the scalars which we can call x, y, and z, such that we are able to write v as a linear combination of u1, u2, and z, u3. So you want to write v as a combination of the given scalars, which scalars we have let to be x, y, and z. Then together you want to show that this v can be written as a combination of these vectors together with scalars. That is by definition. So you must have scalars to get the linear combination of v in terms of u1, u2, and u3. So our scalars, we are letting our scalars to be x, y, and z. So we want to get these defined scalars here. We want to get the value of x, y, and z. And after that, we shall have shown that v can be expressed as a linear combination of u1, u2, and u3. So from here, we are given v. We are given v as 3. I will write it in the column form. We are given v as 3, 7, and -4. We have u1. u1 is 1, 2, and 3, plus y. u2 is here. u2 is 2, 3, 7, is 2, 3, 7, 2, 3, 7, and u3 is 3, 5, and 6. So from here, we know how to deal with such vectors here. So you have 3, 7, -4. you can first multiply scalar inside. We shall have x, 2x, 3x. We shall add there 2y, 3y, 7y. We shall add there 3z, 5z, and 6z. So we can easily get this as 3, 7, negative 4, which is same as, let us add the corresponding entries, that is x plus 2y plus 3z. This will be 2x plus 3y plus 5z. Lastly, it will be 3x plus 7y plus 6z. This is what we have. If you remember very well, if you are equating this to this, if for example you consider in matrices, so for this to be equal to this, then the corresponding entries must also be equal. And for that case, this will give us x plus 2y plus 3z equaling to 3. That will be equation number 1. We shall have 2x plus 3y plus 5z equaling to 7. We shall have 3x plus 7y plus 6z equaling to negative 4. This is equation 2. This is equation number 3. So we can easily solve equations 1, 2, and 3. So solving equations 1, 2, and 3. Use any method of your choice and solve for these equations. We know how to solve this. You can use Echelon form, that is Gauss elimination, Gauss-Jordan. You can use elimination method, substitution method, any method of solving the 3 equations. We have so far looked at how best we can solve 3 equations using various methods. So solve these equations here, 1, 2, and 3, and get the values for x. I will simply get the values for x. X will be 2, y will be negative 4, and z will be 3. So you have to solve this and see whether you are able to get x, y, and z. So here you will have got your scalars, that is x, y, and z. And therefore, you will be able to write your v as a linear combination of u1, u2, and u3 using, this will be 2 in form, that is for x, that is 2u1, y is negative 4, so it will be minus 4u2, then z will be 3, so it will be plus 3 u3. So writing this, we shall have shown that v is a linear combination of u1, u2, and u3. But in case you solve these equations and they have got no solution, if such the solution does not exist, then it means v cannot be written as a linear combination of u1, u2, and u3, since we shall not be able to get these scalars here. So solving this equation, if you get a unique solution, then a unique solution will help you to get these scalars. Otherwise, if the solution does not exist, then it means v cannot be expressed as a linear combination of these vectors here. So that is how we deal with a linear combination. You have to express one vector in terms of others, and you can express this vector in terms of other vectors by using the scalars. So if you are able to write this, then we shall say that v is a linear combination of u1, u2, and u3. Let us now look at another example. So we are done with showing that this v can be expressed as a linear combination of u1, u2, and u3. So basically, we now want to come at what we call example number 2. So in our example number 2, we want to express the polynomial v as a linear combination of the polynomials p1, which is also given as this, p2, and p3. So we want to express v as a linear combination of p1, p2, and p3. So to do that, we must seek for the scalars. We must seek for the scalars. To do that, we must seek for the scalars such that we can write v as a combination of p1, p2, and p3. So if we seek for our scalars, we can let our scalars to be x, y, and z, such that we are able to write v as x p1 plus y p2 plus z p3. So this is what we are interested in. We need to show that v can be written as a linear combination of p1, p2, and p3. And if that is the case, then we shall need to solve for x, y, and z. And after solving for x, y, and z, that will be if x, y, and z exist, then we shall have v as a combination of p1, p2, and p3. If the values of x, y, and z don't exist, then v cannot be expressed as a linear combination of p1, p2, and p3. So let us look at this expression. We are saying we seek for the scalars. We seek for the scalars x, y, and z. We seek for the scalars x, y, and z such that we can have v which is equal to x p1 plus y p2 plus z p3. But what is v? What is p1, p2, and p3? So we already have our v as 3t squared plus 5t minus 5. So we shall substitute for v, p1, p2, and p3 within this expression. So we shall have v. Our v is 3t squared plus 5t minus 5, which is equal to x p1. P1 is t squared plus 2t plus 1 plus y into p2. P2 is 2t squared plus 5t plus 4, then plus p3. Then p3 is t squared plus 3t plus 6. So this one here will be same as multiply x there, xt squared plus 2xt plus x, multiply y here, 2yt squared plus 5yt plus 4y. We are adding zt squared plus 3zt plus 6z, multiplying by z through this. And this will be same as, now we can pick the corresponding coefficients for t squared. So we shall have the coefficient for t squared here is x. The coefficient for t squared here is 2y. The coefficient for t squared here is z. These are coefficients of t squared. Plus the coefficient for t, we have 2x, t 5y. The coefficient for t 3z. The constants, we have x, we have 4y, we have 6z. That is what we have so far. But the whole of this is equal to 3t squared plus 5t minus 5. So we shall equate the coefficients, equating the coefficients, equating the coefficients, equating the coefficients of the same powers, of the same powers of t, of the same powers of t. So this side we have t squared, this side we have t squared. So we shall equate the coefficients. So when we equate the coefficients, it means this 3 will be equated to this. So x plus 2y plus z will be equated to this 3, and this will be equation number 1. Then next, the coefficients for t, these are coefficients for t squared. Then coefficients for t, you will have 2x plus 5y plus 3z, which will be this one here, which will be equal to 5. This will be equation number 2. Then for t to power 0, this will be negative 5, and this side we have x plus 4y plus 6z, which is equal to negative 5. This will be equation number 3. So you have 3 equations and 3 unknowns. You can easily solve these equations and verify. So verify that your x will be 3, your y will be 1, and your z will be negative 2. So solve these equations here and verify that this is true. So if you get the values of x, y, and z, you will therefore say that therefore V can be written as a linear combination of P1, P2, and P3 as 3P1 plus y, y is 1, that is P2, minus 2P3. And this, you will have shown that V can be written as a linear combination of P1, P2, and P3. Next, we will try out this question here. You are given U1, U2, and U3, and they want you to show that whether A equaling to this is a linear combination of U1, U2, and U3. So what you are interested in, you need to seek for scalars. You need to seek for scalars. For example, X, Y, and Z, such that you need to seek for scalars x, y, and z, such that you are able to write A as a linear combination of U1, U2, and U3. So you are interested in showing that there exists X, Y, and Z, such that you are able to write A as a combination of U1, U2, and U3. So you have your U1, U2, and U3, you have your A. So basically, C if you are able to get X, Y, and Z. In case X, Y, and Z, if you solve the system, if you solve a system and you get no solution, if you solve a system and you get no solution, this one means A is not a linear combination. A is not a linear combination of U1, U2, and U3. A will only become a linear combination of U1, U2, and U3 if you are able to define X, Y, and Z. But if you solve that system and you cannot get the value for X or Y or Z, if you are not able to get the value for any of these, or if for that case there is no solution, then you will give your conclusion that A is not a linear combination of the given vectors. So you will try out this and see what it will give out. So that is where we shall stop for today.